Hello everyone, welcome to the presentation of my qualification exam. My name is Himan Namdari and my advisor are Dr. Reza Zekavat, Dr. Oren Mangoubi and Dr. Fabrizio Murai. Today's focus for this discussion is about introducing an innovative use of machine learning to analyze GPR signal for estimating soil moisture in the root zone. So, as we know, accurate soil subsurface characterization is an essential for effective subsurface analysis. And this process is not only fundamental for our study, but also critical for a diverse range of application that can impact everyday's life and global challenges. For instance, in forestry can improve our understanding of wildfire risk. In civil engineering, it contributes to the assessment of structural foundation. And in planetary exploration, soil composition analysis become a key component in search for life. In agriculture, which is our focus today, this technology provides insight to subsurface soil moisture level and at the same time can provide a soil layer profile, which is crucial for irrigation and crop yield optimization. Subsurface analysis method can be categorized in two main categories, invasive and non-invasive. The invasive method, which are including coring, using probes and excavation, and then sending the samples to laboratory to analyzing more in depth, are simple and accurate, but they're destructive, time-consuming, and in many cases expensive. The non-invasive methods such as time domain reflectometry and satellite aperture radar, although they can cover a large area and they're fast and efficient, they do have a limitation in penetration depths, and they cannot accurately delineate farm borders or the region of interest. Moreover, ground penetration radar has been used to estimate soil moisture in farms. This method is non-destructive. It can provide real-time data and it has rapid assessment. There are two main challenges using GPR for estimating soil moisture, which we can dive more in detail in the upcoming slides. Now let's understand how intelligent ground penetration radar can be generated. But first we need to understand what is GPR. The GPR radar is an electromagnetic based radar which propagating an electromagnetic wave using its transmitter, and it will record the reflected signal by using its receiver. This gives us an idea of what will happen to our received signal. In here you can see an example of an A-scan signal or amplitude scan, which is a received signal after penetrating into the soil. You can see there are many peaks and the shape of a signal has been changed with respect to the composition of the soil. Basically, whenever we have a contrast in soil moisture, we expect to have a peak. And higher the attenuation basically means that you have a higher level of moisture change between these two layers. Now, let's dive into intelligent GPR. We want to combine the traditional GPR with machine learning, and this can enable us for having a non-invasive subsurface soil assessment to extract soil composition, soil moisture content, soil anomalies, and more. For doing our literature review, we started with this paper. Their objective was estimating soil moisture using GPR data and an artificial neural network. Their evaluation measures was using MAPI or mean absolute percentage error with the value of 1.23. As you can see from their simulation environment, they do have two main limitations. First of all, their soil layer has been defined in a constant 40 centimeter depth, and they also have an external object, a cylindrical object that will create an hyperbola shape when the A-scan signal will be emitted to the soil. Moreover, their artificial neural network consists of many neurons, and this is due to the fact that they use the actual raw signal, which has up to 3,000 variables, and this makes their model super complex. The last limitation in this project is that they have a small size dataset, which consists of 2096 simple A-scan, and this will result in an accurate soil profiling, which can limit the generalization of their method. The next paper, which is from the same author, They try to classify soil type using GPR B-scan. The B-scan dataset is actually a stacked version of many A-scan signal, and the hyperbola shape that you can see over here is created due to having the same cylindrical object in the soil. So same as their old proposed method, the only difference here is that they use a different type of dataset. Their dataset is still small size. They have 700 B-scan, which will not cover all the possible scenario in the soil. They don't have a real-world data for testing their model. Their CNN architecture is complex, and they used the convolutional neural network to extract their feature, which is using a black box, and the interpretation of the result will be pretty much hard. And also, as I mentioned before, their generalization will not be sufficient due to the fact that they do have a small dataset size. But overall, they got a 97% accuracy to sort of like classify the soil type into 4 types of soil. The last paper has been published by the developer of one of the simulation that I'm going to introduce in this paper, gprMax. You can see a version of their simulation. Still, in this paper, they also have a rebar created, and they're trying to create the same hyperbola shape over here to estimate the rebar radius. Here you can see their error in estimating the rebar radius, which is 12 millimeter. They also use a neural network, and they applied PCA to reduce the number of their training data sets with 8 most dominant components. Given the small size data set, which is 2,000 synthetic data, and the study that was constructed solely for a specific scenario that you need to have a rebar to generate that hyperbola shape, this method is not generalizable, and at the same time, it's not fit to our case scenario, which is estimating soil moisture in megafarm. Therefore, implanting these rebar in all the megafarm is impractical. Overall cons of related approach are limitation in diversity and size of training data, lack of testing with real GPR data, lack of consistency of simulation with soil real scenarios, which usually they use random gprMax parameterization, and their method are not applicable for large-scale operations such as megafarm. Our objective was developing an intelligent GPR-based soil moisture estimation. There are some limitations. Our model needs to have a large amount of labeled GPR data, as we are using a supervised learning model. The data should also be diverse and accurate with respect to the real soil moisture scenario. At the same time, we need to also have some data processing and also some other processing method for interpretation of the data. Our proposed solution is to simulate the real scenario, as you can see in this figure, to create GPR data using gprMax simulation. We would like to extract features through advanced algorithm. This will help us to reduce the size of the training data and at the same time focus more on the most important features. Then we want to apply machine learning to interpret these data sets and predict our soil model configuration, which could be the number of layers and their moisture in general. At the end, we want to use our generated synthetic data to be combined with the real data which we generated in WPI using in a real environment to enhance the accuracy of our model. Therefore, our contribution are as follows: improving the simulation quality, in identifying effective data pre-processing technique, identifying the best ML model that fits the GPR data, applying several feature extraction on raw GPR data to improve the accuracy of the model and reduce the dimensionality, validation with real-world data, and also improving the efficiency and accuracy of soil moisture estimation. In this flowchart, you can see a general perspective of our proposed model. So we would like to know more about our configuration for the signal that has been propagated and also simulation setup. As I kind of like mentioned before, we try to simulate the real scenario, which a drone is hovering over this soil at the height of 2 meters. This GPR technology should be able to send and propagate signal up to 1.5 meters. Therefore, we used simulated data with a scan size of 8,000 features. We generated two types of data set for our layers. One was 100,000 samples, and the 3-layer version was 150,000 samples. We used Ricker waveform with 1.5 gigahertz as our frequency. And based on the hydraulic model, we decided to assign these values. So layer 1 can have moisture from 5 to 15, and layer 3 can have moisture from 26 to 35. The reason behind this selection is that we use the hydraulic model of the soil, which basically the soil moisture will increase with the depths of the soil itself. The propagation time was set to 40 nanoseconds, so we make sure that our transmitted and received signal has enough time to be recorded by our radar. To create our synthetic GPR dataset, we combined and considered a common land model and hydraulic soil model and use it in our proposed HydroCamp algorithm. This is a Python programming algorithm which actually considers the conditions based on these two models and generate that 6 labels that we need to sort of like use to create our simulation in gprMax. And later we use HPC to kind of like create a large scale synthetic data. As you can see, the final data set will have a size of 150,000 by 8,006, where 8,000 are the feature and 6 is our labels, which has been concatenated to the end of each samples correspondingly. A little bit more exploration about common land model and soil hydraulic profile. In common land model, the soil has been defined, as you can see over here, in sort of like 4 layers. The first layer is organic layer. In farm, we don't have much of organic layer. We do have organic layer mostly in forests. Based on this common land model, our selection of 3-layer model was correct and proven. We also use the depth that has been suggested in this model, but at the same time, we try to have a randomized version of the depth of the model so we can cover more scenarios. For the soil moisture hydraulic profile, we know that the soil moisture will be increasingly more when we go deeper. Therefore, we try to apply more moisture in the lower depths with respect to the higher layers. The gpRMax simulation used this 6 label generated by our algorithm in a .n file, which has been fed to the gpRMax. And when the simulation is done, we repeated this simulation 150,000 times to make sure that we have enough data. We then applied zero-time correction, normalization, and time gain adjustment to make our data more valuable. And at the end, we try to check our label balancing to make sure that all the scenarios that has been generated using these 6 values have the same repetition of simulation. So our model is not going to go overfit with respect to one of the scenarios. Our first step after generating the data was pre-processing the synthetic data, as I mentioned before. But we wanted to know which type of machine learning model will have a best training result. Therefore, we used several multi-regression models, and we evaluate this model result based on their root mean square, average root mean square in prediction of those 6 values, and also the training time. After this, we selected the best model with the lowest RMSE and lowest training time, which was random forest. And then in next step, we used the synthetic data and applied some feature extraction so we can generate more feature sets that can help us to reduce the dimensionality of our data set, and at the same time, it can focus more on the most important features. Here is the first extraction method using descriptive statistic. We used the ASCAN data using Python programming. We wrote a code that will literally take all the descriptive statistics such as mean, max, STD, skewness, kurtosis, and also quartile percentile 1 to 4. We then fed this new data set into an RF model to find the top 5 most important features. The reduction is from 8,000 to 5. Then we use ANOVA method or analysis of variance. This method will categorize or group the each indexes in each sample, and then it will start to compare these group with the other group and inner groups to make sure at the end we have an F and P value as a result. The P value indicates the importance or the variance of that specific index. As you can see, some of the indexes in the ASCAN signal has been indicated with a higher value of F, and this indicates that these values have low value of P, which is basically helps us to get a better result. So we sort them out and we extract the top 100 of them. Again, we fed this to our descriptive statistic methodology, and we reduced the dimensionality of our input data from 8,000 to 10. The last feature extraction method, which has been proposed by us, and based on my knowledge, it has not been used before specifically for soil moisture estimation, is a combination of peak detection. So we use the ASCAN data again, we use the Python code that is a library in Python that has like a dynamic threshold, and you can select a different number of peaks based on different values. We adjust this value to find the most important peaks, and then we use the information such as the index of the peak and their amplitude, the distance between them, and also the area under each of their curves. And we fed that again to a descriptive statistic model to select the top most important 10 features. So reduction here was also from 8,000 to 10. So overall, you can see in the table, using the raw data set and fed it to different feature extraction method, including PCA, we will have a large amount of reduction rate, specifically in case of PCA and peak extraction, which is almost 99%. For feature analysis and soil moisture estimation, as we mentioned before, we generated a new reduced size of different feature extraction method, which result in different feature set. We use this feature set and we use the RF selected model, use this data set to train this model, and then compare their result in root mean square and training time again. So we can select the best prediction result based on this analysis. Here is the result for machine learning model selection and evaluation result. As you can see, we used several multi-regression problems, and we used the raw data set here, just pre-processed using normalization, to create their train RMSE and test RMSE values, and at the same time training time. Among these methods, as you can see, random forest has the lowest RMSE. It doesn't show overfeeding, and at the same time, it will also have a high training time. Therefore, our proposed model to reduce the dimensionality of the data will work here and can help us to reduce this training time and improving the root mean square as well. So as I mentioned before, each of these results is with respect to a specific feature extraction methodology, such as PCA set, ANOVA set, and descriptive statistics set. And also we have the raw data set. The raw data set using the random forest model has been overfeeded. You can see over here that this model has been overfeeded. With the reduction and also extracting those features, ANOVA shows the lowest root mean square both in training and testing. And it also shows the lowest training time. So eventually our results shows that ANOVA is a promising method that can extract the features from GPR data by providing the lowest root mean square error and also the lowest training time with respect to even common standard models such as PCA that you can see over here. Our future work is try to enrich our data and improving our results. This way we would like to create some real data with respect to our synthetic data set and our simulation. We would like to combine these two data sets with several approaches, train the RF model and do the performance and prediction analysis. And eventually we would like to use this improved version of soil moisture estimation platform to create our soil map. Here is a representation of our real data collection setup at WPI. We use two stands to mimic the same scenario of a hovering drone coupled with a GPR signal. And we are using 1.5 gigahertz using an SFCW radar with the same 40 nanosecond of propagation time. As for conclusion, we developed a machine learning framework to improve soil moisture estimation using GPR. We also generated a large, realistic GPR dataset using gprMax simulation. We introduced new feature extraction method, enhancing ML model training and accuracy. We also, our proposed method shows a promising result for a broader application in agriculture and more. And as I mentioned before, our future work is an iterative refinement with real-world data, improving the model prediction. Here are the references that has been used in this slide, and I would like to thank you